Welcome to our comprehensive calculus lesson on derivatives. In this video, we'll cover four important topics: the product rule, the quotient rule, derivatives of trigonometric functions, and how derivatives represent rates of change. Let's get started. Let's begin with the product rule. When we have two functions multiplied together, and we want to find the derivative, we need a special rule called the product rule. The product rule states that if u of x and v of x are differentiable functions, then the derivative of their product equals the derivative of u times v plus u times the derivative of v. In mathematical notation, we write the derivative of u times v equals u prime times v plus u times v prime. Here's an intuitive way to think about the product rule. When you have two changing quantities multiplied together, the overall change depends on how each quantity changes. Think of it like this: the total change is the sum of 1. How much u changes while v stays the same, and 2. How much v changes while u stays the same. Let's work through an example to see the product rule in action. Example 1. Find the derivative of f of x equals x squared times sine of x. First, let's identify our parts. U of x is x squared, so u prime of x is 2x. V of x is sine of x, so v prime of x is cosine of x. Now let's apply the product rule. F prime of x equals u prime times v plus u times v prime. F prime of x equals 2x times sine of x plus x squared times cosine of x. So our final answer is f prime of x equals 2x sine of x plus x squared cosine of x. Now let's move on to the quotient rule. The quotient rule tells us how to find the derivative of a fraction with variable parts in both the numerator and denominator. If u of x and v of x are differentiable functions, and v of x is not 0, then the derivative of u over v equals u prime times v minus u times v prime, all divided by v squared. In mathematical notation, the derivative of u divided by v equals u prime times v minus u times v prime, all over v squared. Let's solve an example using the quotient rule. Example 2. Find the derivative of g of x equals the natural logarithm of x divided by x cubed. First, let's identify our parts. U of x is the natural logarithm of x, so u prime of x is 1 over x. V of x is x cubed, so v prime of x is 3x squared. Now let's apply the quotient rule. G prime of x equals u prime times v minus u times v prime, all divided by v squared. Substituting our values. G prime of x equals the quantity 1 over x times x cubed minus natural log of x times 3x squared, all divided by the quantity x cubed squared. Let's simplify. G prime of x equals x squared minus 3x squared times natural log of x, all divided by x to the 6th power. Further simplifying, g prime of x equals x squared times the quantity 1 minus 3 natural log of x, all divided by x to the 6th power. So our final answer is g prime of x equals the quantity 1 minus 3 natural log of x divided by x to the 4th power. Let's now explore the derivatives of trigonometric functions. There are 6 basic trigonometric functions, and each has its own derivative formula. Here are the 6 fundamental trigonometric derivatives. The derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. The derivative of tangent of x is secant squared of x. The derivative of cotangent of x is negative cosecant squared of x. The derivative of secant of x is secant of x times tangent of x. And the derivative of cosecant of x is negative cosecant of x times cotangent of x. These derivatives are essential to know and can be visualized on the unit circle. Let's see how the derivative of sine, which is cosine, relates to the rate of change of the sine function. Let's work through an example using trigonometric derivatives. Example 3. Find the derivative of h of x equals secant of x times tangent of x. For this particular example, we could use the product rule with u equals secant of x and v equals tangent of x. But actually, we can notice something interesting. This expression, secant of x times tangent of x, is exactly the derivative of secant of x. Looking back at our list of trigonometric derivatives, we see that the derivative of secant of x is secant of x times tangent of x. Therefore, the derivative of h of x equals secant of x times tangent of x is simply h prime of x equals secant of x times tangent of x. Alternatively, we could have used the product rule with u equals secant of x, u prime equals secant of x times tangent of x. And v equals tangent of x. V prime equals secant squared of x. Applying the product rule, h prime of x equals u prime times v plus u times v prime, which gives us secant of x times tangent of x times tangent of x, plus secant of x times secant squared of x. We can simplify this using the identity tangent squared of x plus 1 equals secant squared of x. But directly recognizing the derivative from our formula list is much simpler. Finally, let's discuss one of the most important interpretations of derivatives as rates of change. The derivative f prime of x represents the instantaneous rate of change of the function f with respect to x. This is a powerful concept with many real-world applications. Here are some common interpretations. If f represents position, then f prime represents velocity. If f represents velocity, then f prime represents acceleration. If f represents the cost of producing x items, then f prime represents the marginal cost. Let's solve an example involving rates of change. Example 4. A particle moves so that its position at time t is given by s of t equals 5t cubed minus 2t squared plus 4t. Find the velocity v of t and the acceleration of t. For velocity, we take the first derivative of the position function. V of t equals s prime of t equals 15t squared minus 4t plus 4. For acceleration, we take the derivative of velocity of t equals v prime of t equals 30t minus 4. Let's interpret what this means physically. At time t, the particle's velocity is given by 15t squared minus 4t plus 4. Its acceleration is 30t minus 4, which means the acceleration increases linearly with time. For example, at t equals 2 seconds, the position is 5 times 2 cubed minus 2 times 2 squared plus 4 times 2, which equals 40 feet. The velocity is 15 times 2 squared minus 4 times 2 plus 4, which equals 56 feet per second. The acceleration is 30 times 2 minus 4, which equals 56 feet per second squared. Let's summarize what we've learned today. We covered 4 important topics in calculus. First, the product rule, which states that the derivative of u times v equals u prime times v plus u times v prime. Second, the quotient rule, which states that the derivative of u divided by v equals u prime times v minus u times v prime, all divided by v squared. Third, the derivatives of trigonometric functions, including the derivative of sine is cosine, the derivative of cosine is negative sine, and many others that we need to memorize. Finally, we learned about derivatives as rates of change. The derivative represents the instantaneous rate at which a quantity is changing. In physics, this gives us velocity and acceleration. These concepts form the foundation of calculus and have countless applications in physics, engineering, economics, and many other fields. Practice these rules, and you'll develop a strong understanding of derivatives.